Hey class, I hope you're all doing well. We are officially halfway done with fourth quarter. We only have 5 more weeks to go after this. So good job to everyone. Most of you are getting your work in. Like last week and the weeks before that, we're doing another ed puzzle for our main notes, our main content for the week. So no shakeups there. So I just wanted to remind you that all work is going to be assigned on Mondays through Fridays, but it's going to be different a little bit for the next couple of weeks. Week we are going to have work due on Thursday instead of Friday because we're going to have a short week. So work I'm assigning today, which is Monday, due Thursday. And then next week, I'm not going to put out work on Monday. I'm going to put out work on Tuesday, and it will be due Friday next week. So this week's work is due on Thursday. Okay. Um, every week, I'm holding a Google Meet. It's always at the same time. So every Wednesday at 10 a.m., I'm holding a Google Meet. Last week it went about 40 minutes. If more people are jumping on and we're talking about science, I might make it longer. If it's just a few people and we're not really staying on task and we're just being social, it might be a little bit shorter, maybe half an hour. But definitely hop on if you want to see your classmates or talk science. So we're still continuing with weather. We might get to one or two topics today. So I want to talk about number one, the Coriolis effect. It's kind of a cool phenomena that occurs on Earth because it's spinning. So we're going to get talking about that right now. So let's switch to the notes. So our main topic this week is called the Coriolis effect. Basically, the main idea you want to get from the Coriolis effect is objects or things in the northern hemisphere as they move deflect to the right. They don't actually go, they don't appear to go in a straight line. They deflect to the right. And in the southern hemisphere, it's exactly opposite. Things in the southern hemisphere appear to deflect to the left. Okay, so this could be like a flying airplane. This could be anything large moving over a large scale, trying to go in a straight line is always going to deflect to the right. But this isn't like throwing a baseball. That doesn't go long enough or far enough to be affected by the Coriolis effect. But things taking a really long trajectory over a long period of time, or it doesn't even have to be a long period of time, but just a long trajectory, like these lines here on the map show pretty long trajectories. If they're trying to go straight for a long time, they get deflected to the right. Now you might be wondering, why is this? Well, this is caused because Earth is a sphere that's constantly spinning, right? We have two poles and then the Earth spins around its axis, okay? At the equator, your objects or things have to go a greater distance in one day, right? They have to go around the whole Earth. They go around the entire equator in one day compared to things near the poles, which only have to go a short distance. And at the poles, you don't even travel any distance at all, right? You're spinning on that one spot. You're not traveling any distance. So these objects at the equator are actually moving much, much faster than the things at the poles. You might be wondering, well, why does this make them turn different directions on Earth, right? Well, as these things that are going super fast go trying to go a straight line up towards the poles, they get deflected to the right because they're actually spinning, they're moving faster than the things around them. So instead of going straight, these things want to go farther, right? So if they start at the equator and they're going up towards the poles, they're actually moving faster than the things around them. So they're going to move to the right because the Earth is spinning this way. They're going to get deflected to the right. They're moving faster than the things around them. So you can think that they're moving ahead. Similarly, if they're going slower, right, they're up towards the poles and they start heading towards the equator, they're going slower than the things around them. So as they head down towards the equator, they're actually going slower than the ground beneath them, you can think. And they look like they're falling behind, right? They're going to the right still. They're still deflecting to the right, but that's because they're going slower than the things around them. So the big idea is things in the northern hemisphere deflect to the right, and things in the southern hemisphere deflect to the left. So let's look at this picture a little bit bigger. So in the northern hemisphere, so the Earth is going this direction, west to east. So objects deflect to the right in the northern hemisphere, and it's just flip-flopped in the southern hemisphere. They're still going the same direction, right? They still want to go west to east if they're going towards the poles, and east to west if they're going towards the equator. Okay, so things in the southern hemisphere deflect to the left. Things in the northern hemisphere deflect to the right. Okay, so those are our big ideas. Northern hemisphere deflect to the right. Southern hemisphere deflect to the left. That's the big thing I want you to remember. So if you look at this Earth here, all these arrows are showing how things are deflecting. So if they're going towards the poles, they're deflecting to the right. Well, they're always deflecting to the right, but they're deflecting this way. If they're going towards the equator, deflecting this way. In the northern hemisphere, always deflecting to the right. Southern hemisphere is always deflecting to the left. Now, I know I talked about airplanes and things like that, but those aren't the only things that have those long trajectories, right? We talk about weather and air masses for the last couple of weeks. Air masses are the same thing. If they start traveling north or south, they get deflected to the right. Okay, so either this week or next week, we're going to talk about why do weather systems spin, and like hurricanes. Why do hurricanes spin and things like that? Well, that's because of the Coriolis effect. Okay, so big takeaways in the northern hemisphere: weather system, air, objects, they deflect to the right. Things in the southern hemisphere deflect to the left. Now remember, this is just going over a long distance. This isn't like throwing a baseball. This is like airplanes that go to the right, or like weather that goes a long distance, okay? So let's watch a quick video on the Coriolis effect, maybe to help you out a little bit.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around...
Okay, so that was the Coriolis effect. That's the only topic I think we're going to add to this week, because it's kind of hard to wrap your brain around, right? Big takeaways: things or air or anything moving over a long trajectory is going to deflect to the right in the northern hemisphere. And remember, the northern hemisphere is where Minnesota is, right? Northern half of the Earth. We're closer to the North Pole compared to the South Pole. So we're in the northern hemisphere. So everything in our hemisphere, where Minnesota is going to deflect to the right. Everything in the southern hemisphere deflects to the left. Okay, so that's pretty much our big takeaways, and this is due to the Coriolis effect. Next week, we're going to continue with weather, at least for one more week, possibly two. Like I said, this is the halfway point, guys. You guys have done pretty great so far. We have one more assignment to finish out the week, and that is going to be you tracking the direction of the wind. So we're going to tie in Coriolis effect and all that stuff with actual weather as you track the wind. We're going to tie it all together next week. But for this week, I want you to track the direction of the wind for at least 5 days, okay? So like I said, this assignment is due on Thursday. We don't have school Friday. We don't have school next Monday. Okay, so expect your next lesson to be posted Tuesday next week. We have a Google Meet every Wednesday at 10 a.m. So 10 a.m. this Wednesday, hop on to Google Meet and we'll talk science or just drop in and say hi. So look forward to seeing you guys there. If you have any questions, send me an email. I hope you have a great rest of your week.